The other transformations will make it easy for us to go between the real world and the Laplace world, so that we can translate our problems. All right, let's do an example. Hopefully you guys are kind of familiar with some of this stuff already. Let's do maybe number 38. It's 7.2. We're kind of wrapping up 7.2. And so these Laplace transformations allow us to solve initial value problems where the initial value is kind of embedded in the problem. So what do? First, we look at the problem and say, okay, we're in the real world with t's. We're going to translate this to the Laplace world with s's. So let's do that. So this is our Laplace transformation. So the y double prime we get to use this this transformation. So y is the name of our function. So when we translate the names of functions into the Laplace world, the convention is to use capital letters. So little letter y is in the real world, and now capital letter y is going to be in the S world. So we have s to the n matches the derivative, the number of derivatives. In this case, we just have the second derivative. So we're going to start off with s to the second power, and then we have y. And this is how I'm going to write my capital Y, just so it looks different from a lowercase y. I don't know if it'd be good to use the parentheses s there. I'd say it's y of s, but I'll put that there for now. Minus, and then we take s, one less power for s to the first power, and then we have y of 0. And then we keep going until we go to the n minus first derivative. So we went to the second derivative. This is a y double prime, so n is equal to 2. So we're going to go one more, and this time it's going to be s to the 0th power, or just 1, and then y prime of 0. Your s's are moving, the powers for s's are moving down, and then here you start off with a y in the transform world, and then you have y sub 0, y of 0, and y prime of 0. Your derivatives are going up. Yeah, it's going in opposite direction. So your derivatives are going up, and your powers for s's are going down. Yeah. It's the s to the first power, y of 0. Is that what you're talking about? This would be s to the first power, yeah. And then technically there's an s to the 0th power, but we don't put that down. So this is our y double prime. Oh, we don't have a y prime, so we just have a plus 9. Y of s. Okay. So e to the t, we transform e to the t, that's a is equal to 1, so this is going to be 1 over s minus 1. Okay, so now we're in the Laplace world. Okay, so in the Laplace world, we're done with calculus. We're just going to use algebra, and for algebra, we're going to want to solve for the y function that we're looking for, capital Y, and so that we can translate that back. Now, we also have from the real world some of these initial conditions that kind of make things nice for us. Y of 0 is equal to 0, and y prime of 0 is also equal to 0. So those things disappear. That makes for, looks like it makes for an easy thing to solve for. So let's do the algebra. We have s squared, capital Y of s, plus 9, capital Y of s, is equal to 1 over s minus 1. And then we factor out the y of s, and then divide by s squared plus 9. And then we have, we've done the algebra, so we're done. Well, kind of. So remember that picture that we had where we're in the real world, and then we're in the Laplace world. And then we went to the original problem, and then we went to the Laplace world with an algebra equation, and then we do algebra, and then we solve for this. So we do the algebra to solve for this, and then we need to go back to translate this back to the real world through the inverse Laplace transform to get our solution. So instead of using calculus to solve for this in the real world, we go to the Laplace world to use algebra to solve for this. So that's the basic idea, and now we need to take that one step back. And for that, we want to look back at our list of formulas and say, okay, the equation, the function that we have here does not look like any of these. And so it kind of looks like a couple of them, but we need to break it apart. And so we need to use partial fractions to split this up. So let's, on our way to solving for this or bringing it back to the real world, we need to set this up as a partial fractions. Now, s squared plus 9 is an irreducible quadratic. You cannot factor this into linear factors, so it's a second degree polynomial, which means the numerator should be a first degree polynomial, linear, whatever you want to call it, bx plus c. And then I'm just I'm just going to not deal with that and expect you guys to research your own partial fractions. Probably. So s minus 1, s squared plus 9. So we have this result now where we can take a look at each term, and each term looks like one of those things, one of those Laplace transformations that we did. The only thing that we probably need to consider is to take a look at this expression over here, because there's no expression where we have a linear and an irreducible quadratic down in the bottom. So we need to split this up into a couple of pieces. So I would probably consider this as negative 1/10 times 1 over, or times s over s squared plus 9 minus 1/10 1 over s squared plus 9. And then this, if I want to rewrite it, that's just 1/10 times 1 over s minus 1, so that I could take a look at each of these. Because the Laplace transformation is a linear transformation, we can split this up into the sum of things, and then any constants that I have will just remain as constants when I transform it back. Okay? So from here, we do our inverse Laplace transformation to get our solution. And that is going to be y of t. So we're in the real world now. We bring this back to the real world. And we have, I guess we'll look at it in the order that it's written here, negative 1/10. And then the s over s squared plus 9, remember that translates back into sine or cosine? Sine? Cosine? So the 9 is actually 3 squared, so that's the coefficient of the angle. So what did you say, cosine? Cosine 3t minus 1/10 sine 3t. And then our last one over here is going to be the exponential function again, plus 1/10 e to the 1t, right? So the negative is built in. Okay? So that's it. So if we didn't do it this way, we would have had to found the homogeneous differential equation. The solution for that would give us our functions, our called fundamental solutions, and then because it's not equal to 0, we would need to assume that we can use either undetermined coefficients or the other one, variation of parameters, to solve for this. But now we got it a little bit quicker using Laplace transforms. Okay, questions? All right. So moving on, things aren't always going to be this easy, of course, so we need to prepare for other things that we need to deal with. So this is 7.3, I guess. We're gonna take a look at some shifts, or at least function-wise, they look like shifts. And the first one, they call it the first translation theorem. So there must be a second one. The translation theorem here happens in the S world, where there's a shift in the S. And for that, we see that the transformation for e to the AT times a function f of t is going to result in a function in the S world that has been shifted by a units to the right. This is more importantly used for the inverse Laplace transform, because there might be some times where we're going to see a function in the S world that we want to translate back to the T world, and it looks like that function is similar to one of the original functions that we looked at, except it's been shifted somehow. And so when that happens, we'll need to apply this shift theorem, and so that we can translate it back. Let's take a look at an example. Um, let's try to do 24. So again, our first step is to translate into the Laplace world. So let's do that. We'll do our Laplace transformation, and we'll remember how to translate a second derivative function to the Laplace world. So it's s squared capital Y minus s to the first power times y of 0 minus s to the 0th power, which we won't write down, y prime of 0. Okay, now we'll translate the first derivative over, so that's s to the first power times y of 0 minus, and then the s's are gone, so it's just y of 0 plus 4 times y, oops, this should be y, capital Y of s. So that's my left-hand side, and my right-hand side is a function that I need to translate, and I look at that function and say, hey, this is like this transformation theorem, right? So let's see how we can translate this. Let me rewrite this as according to, they have the exponential function first, so let's write the exponential function first, times t to the third, and t to the third is going to be our f function. And so as that gets translated, it becomes f. Now, we need to know the transformation of t cubed. And if you remember the transformation of t cubed, you take the power, and then it's I forgot. It's what? So 3 factorial s to the 4th. So we can call it 6, or you can call it 3 factorial. Let's call it 6 over s to the 4th. But now our s gets translated, right? So the translated are, instead of saying s, it's going to be s minus whatever the translation is. And so what's a translation? The translation is the coefficient of the power of the exponential, which is 2. So it'll be 6 divided by, and then s minus 2 to the 4th power. Okay? All right. So let's identify, just in case we're not sure about what happened. So this is our transformation from the real world to the Laplace world. And so now we're in the Laplace world. And we're going to do some algebra. And so we want to solve for the s, the capital Y of s's. We also know from the real world that we have some zeros going on here. That's nice. They're both equal to 0. So that's all gone. And so all we have left is s squared capital Y of s plus 4s y of s plus 4 y of s is equal to 6 over s minus 2 to the fourth. And then if we get, yeah, did I miss something? Oh. Yeah. Times e to the at. When actually not just that, but we'll see in the translation back, we're going to need to consider a few of these things. Yeah. Or e to the t times either something else, like a sine or a cosine, or in this case, a polynomial, t cubed. Yeah. Yeah. Now, the other tricky part is that you're trying to get this straightened out, right? The difference between this and the problems that we've been doing. As we do more and more problems, you'll see that there's going to be different approaches for different problems. So there might be a problem where this might be a good approach, but then there might be something else that we're going to learn that might also be a good approach. So you're going to have to decide what approach you use. And don't get too comfortable with one of them and say, I'm just going to keep using this because maybe for another problem you won't be able to use something like that. Yes, there might be another method. Matt, thank you. Alex? Oh no, that's a oh that's an arrow. All right. So we good? We factor out the y of s, and then we divide by whatever's left over, and so we get y of s is equal to. Now this is going to be 6, and then s minus 2 to the fourth times s squared minus 4s plus 4. Okay. I wonder if we can factor. Can we factor that one? You know what? I don't care. I'm just gonna like Wolfram Alpha do it. Oh, it's s minus 2. So 6 over s minus 2 squared, and there's 4 of them already, so it'll be this to the 6th. All right, done. Well, almost done. So now we need to translate it back to the real world. So we're done in the Laplace world. We solved for the equation. We found y of s. So that's the algebra part. That's supposedly easy. And now we need to translate it back. We only have one factor, but it's to the 6th power. But then we also get this this theorem that we have that says that if we can identify this as a function that has been shifted, then it looks like we can translate it back using this special theorem, translation theorem. So we have, this is actually 6, well, let me see if I can do this properly. S, there's no negative there. So s to the 6th, and what do I want in the numerator? I want 5 factorial in the numerator, right? So I want 5 factorial in the numerator, so I need to divide by 5 factorial and then have the 6 that was originally there. So 6 divided by 5 factorial is my constant that's sitting out. So this is the function that I want to translate from to. to, from. And this has been shifted t to the fifth power, yeah, with an extra exponential. So this is what I want to translate. So that's what this is equal to. That 6 divided by s minus 2 to the sixth power is equal to, it's equal to this thing, and I want the inverse transformation of that. So according to this, uh, 5 factorial divided by s to the sixth is t to the fifth, translated back to the real world. So I have t to the fifth power. And then because this has been translated in the s world, I need to multiply this by e to some power. So e to what power? E to the negative, or should be positive, yeah? E to the 2t. So that's, oh, yeah. So 5 factorial is 5 times 4 times 3 factorial. 6 is 3 factorial. So 5 times 4 is 20. Okay. So that's it. I think we're done. Wait, say it again. Yes. Yeah. So I'm kind of doing two things in this one step. I'm doing the shift by writing it like with this vertical bar, S goes into S. So that's it. Not bad, huh? Let me see if I can. Yeah. It's a good thing you guys took Calc 2. So I'm looking for another one where you might have to complete the square, because that happens, or something like that. Uh, if you look, if you guys take a look at 28, can you factor? You can't factor that. Does that give you real solutions? 2x squared plus 20x plus 51. Is that imaginary number, or I'm just looking for a good example, another example. 2x squared. No, but oh, equals 0. Let's see if it knows to solve. Solve, solve. Yep, imaginary number. All right, let's do this one. Let's do number 28. All right, so let's take this and transform it, translate it into the Laplace world. So we have two. Wait, do I want to do this? Yeah, I want to do this. Oh, I was looking at this 0. I was excited about this one, but all right, well, let's deal with it and see what happens. S squared capital Y S minus S times Y of 0 minus S, minus Y prime of 0 plus 20 S Y of 0, Y of S, sorry, minus Y of 0 plus 51 Y of 0, Y of S. Keep getting mixed up with that. All right, we are in the Laplace world now. Right. So let's before we do the algebra, let's knock off some of these guys, or one of them. That's it. So this is a 2. This is a 2. Oh boy. It's only algebra. Stay calm. 2 2s squared y of s minus 2s plus 20 sy of s minus 2. Y prime of 0 went away. Y of 0 became 2, and that became a 2s here. Should be 4. Thanks. All right. So now we need to solve for y of s, and we got a couple of terms that don't have a y of s that we can bring over to the other side. So we'll bring that over to the other side. We're going to get a positive 4s minus 2 brought over to the other side becomes a plus 2. And then each of the y of s's, we'll just have that as a factor that we're going to divide out. So instead of me writing all that stuff here, what? Ah, geez, 40. Thank you. Do I need to erase this too? Does that look okay? All right. When I do videos, I have to make these things correct the first time, and then otherwise I have to start the video over. In class, I just make all these mistakes and you guys correct me, so it's easier to do things in class than videos. All right, where are we at now? So we have 2s squared plus 20s plus 51. All right. Oh boy, what? What? Oh, so I already checked in Wolfram and found that this gave complex roots, right? Um, could. I don't know if that'll work. All right, so now I don't know. Let's try something. Yeah. Uh, closer. Not, still not quite though. Oh, complete the square. Let's do that. How do you how do you complete the square? Um, so make this 50 plus 1, and then factor out a 2 from here. And then, so you, is this a perfect square? Oh, we didn't really even have to do, right? We didn't really have to do the divide by 2 business because I guess Ali already saw that 50 and 50 plus 1 had something going on here. But sometimes you might have to actually do the completing the square. You take the middle term, divide by 2, you square it, add it to add, subtract. All right, whatever. We got to this. S plus 5 squared, right? All right, so I suppose I should show you because I'm not going to do another problem in this section. So if you didn't catch that nice setup, you would still need to factor out from these two, you'd still need to factor out a 2. So the work that I would do, I would have done here if I didn't see it right away, would be 2 s squared plus 10s plus 51, right? And then inside here, I would need to add a 25. So I take the middle term, 10 divided by 2, and then square it. So that's going to be my perfect square number. So that's going to be 25. So I have 2s squared plus 10s plus 25. Now I have 51, but I also have to subtract the 25 that I added in. Now, unfortunately, I didn't just add in a 25, right? I added in a 25 times 2. So I technically added 50 to this expression, so I need to subtract out 50. And so that is going to give me the same result. Now I have 2 parentheses s plus 5 perfect square, and then 51 minus 50 is 1. So that would have gotten me the information. So if you didn't see this splitting up the 51 into these easy pieces, then this is how you would complete the square. All right? Still algebra, right? I mean, we learned this, what, when you were in 3rd grade or something? All right, whatever. So, okay, so now we have 4s plus 40. I probably want to split this up since my Laplace transforms only don't have linear terms on top. But I also need to know what's below here. 2s plus 5 quantity squared plus 1. So I have a 2s plus 5, and then I have this extra s sitting out here. Now, I think I'm going to want an s plus 5 in the numerator also, because if you look at one of the formulas that we have, it's I'm looking at the cosine formula where you have s divided by s squared plus k squared. But the denominator has a shift in it in s. The denominator has an s plus 5 shift, and so I'm going to want the numerator to also have an s plus 5 shift. Okay, so let's take a look at how that's going to happen. So down here, I want S, or 4, S plus 5 shifted. Now, I don't want to change the numerator's expression, but I do want to have an S plus 5 there. So I essentially added a 5. No, I essentially added a what? 5 times 4. I essentially added a 5 times 4, so I need to subtract a 5 times 4. 20. Who knows what's going to be on the exam? So it's the whole idea of adding and subtracting something. Again, it's just algebra. Adding and subtracting something to make it look like something else that you want it to look like. And so I added a 5 times 4, and so I need to subtract a 5 times 4 from the 40, from the numerator, essentially. What? I want to get an S plus 5 up there because the denominator has an S plus 5. And so after I do that, then I can split this up into two different formulas. So we have a 4, oh, so that's a 2. Okay, so now my y of s, I still haven't translated back. I'm still doing some cleanup here. I have a 4. Oh, there's still a 2 in the bottom. Yeah, I have to factor out a 2, but then that's going to give me a 1/2. So let's simplify the numerator. We got 4. Can I? I don't think I could do that. Oh, wait, 40 plus 40 minus 20. That's 20, right? So if I take a 2 out of 1, I'm forced with a 1/2 there. Because I took a 2 out. I took a 2 out of the 1. Yeah, so now I can divide all this by 2. So this is a 2. This is a 210. So now I have a 2 times s plus 5 divided by s plus 5 squared plus 1/2. And if you really want to split the 1/2 up, it's actually parentheses 1 over the square root of 2 to the second power. That's going to be your k. Yeah. It's coming. Yeah. So I want this split so that one of them is going to be the sine, the other one's going to be the cosine. Well, you get to practice between now and yeah, and you get 2 pages of notes. 2? All right, 2 pages, whatever. So, no. All right. So we're there. We're done, almost. So the only thing we need to do is we need to realize what functions we're working with. And so there's going to be essentially a shift of plus -5. So this is going to be your f of s function for each of them, where s turned into s plus 5. Or maybe if you want to, make sure it's related to the formula, it's s minus -5. is what we have. It's the shift that we have. So we know that the e power is going to be -5. So the inverse transform of this is going to be e to the -5 times, or e to the -5t times whatever your function turned out to be. And one of them is going to be a sine, the other one's going to be a cosine. No, the shift tells us it's going to be an exponential function involved in our answer, and then the main function that we're translating back is 1 over s squared plus 1/2, which is, in this case, that's the sine, right? Sine, cosine. So here's your translation back. Y, so this is your translation back, your solution. Y of t is equal to, the first one has a coefficient of 2, and the translation back goes to an e to the -5t, and then the s over s squared plus 1/2 is going to be a cosine, and the k is the square root of 1/2, which is either √2 over 2 or 1 over, that's inside of the angle. So 1 over square root of 2t. And then the other one is 10 times, and then the translation back where you have a constant. Wait, does this have to be k? It has to be k. So messed up. Not quite messed up. Yeah, okay, I messed up. So I want this number here not to be a 1, but to match this number. So this is a 1/2. And so what does this have to be? 5 or 20? Oh, 20 times 1/2 is 10, right? No. What? No, it's not. It's not. What is it, Matt? It's what? It should be this is k squared, and so we need the k itself. So this is 1 over √2. So this is not, so the 10 that used to be there becomes a 10 √2. Because if you multiply 10 √2 times 1 over √2, you get the number that you want, which is 10. Yeah. So make sure we put a 10 √2 there times e to the -5t, and then this is a sine. Okay, done. Okay, we good? Even if you're not good, we need to move on. And if you're not good, then practice, homework, friends, family, I don't know, whatever. YouTube, go to YouTube. All right. So this is a translation in the S. So because they specify this translation in the S, it must be a translation in the T. So translations, by the way, are the easiest ones to deal with because that's like e to the some power. That's what it turns out to be, because if you put that into the original Laplace transform formula with the integral, you'll see that the e's will just multiply each other and then whatever. Translation in the t-axis. Actually, before we go into the translation in the t-axis, let's define another function here. Why don't I just copy everything over? Yeah. Oh, 2. So 4, 4 minutes, 6 minutes. All right. Uh, for us to talk about a translation in the t-axis, we begin first by talking about a type of function. There's 2 special types of functions that we need to get a good handle on in when we're dealing with Laplace transform. The first one is uh, is the unit step function, sometimes denoted by a script u or maybe just a regular capital U. U parentheses of t of a is basically um, a 0 for anything that's less than a value, whatever a is, and then 1 for everything beyond that. So just a picture of this would look something like this. This is your t-axis, and then let's say a is over here somewhere. Your function is going to look like it's equal to this, and then equal to that. So it's a unit step function. Oh, this is 1. There's going to be another important function that we're going to study, I guess, next time. It's called the Dirac delta function. But this is a step function, allows us to do some shifting in the t-axis. So this is the definition of the unit step function. So the Laplace transform of this, if you were to put this into the Laplace transform formula, it goes from 0 to infinity, right? So because this splits up between minus infinity to a and then a to positive infinity, technically you would split up that integral and then you'll get something like this. So the Laplace transform of a unit step function is e to the negative as divided by s. Now notice the translation in the t-axis when it goes into the s world, it's actually the negative of a. So take a close look at the translation in the s-axis and how it affects the e power or the e function, and this translation how it affects the s. Generally, we're not going to simply have a unit step function there. We're going to have a unit step function being multiplied by another function, or more generally, a piecewise function. So a piecewise function where you have one function, the function is equal to one function for a certain amount of time, and then after that, it's going to equal to a different function from another certain amount of time. And so it's usually 0, and then it equals to a function. And so that has to be translated for us into the unit step function so that we can do the transformation properly. And this f of t broken up to g and h functions is going to equal to g of t minus g of t times u of t minus a, whatever that first break is, plus h of t times u of t minus a. And so more generally, so this is just the Laplace transform for the unit step function. But if you have a unit step function that's being multiplied by another function, then your Laplace transform would be e to the negative as times whatever f of s is. Now, if you imagine the original unit step function, this is really the unit step function times 1. And you remember the Laplace transform of 1 is 1 over s. And so this is how they get the 1 over s here. Okay? So more generally, your Laplace transform would look something like this. And usually when you do a shift in the t world, there is going to be some shifting going back to the s world. And so in that shifting going back to the s world, we're going to need to use the step function. Well, there's no time to do an example because you guys have to fill out a survey for me. And so what I'm going to do is I'm just going to continue next time. All right. All right. So practice. Look at YouTube. I can make last year's videos of my lectures available for you if you want, and then you can view those, see if it'll help. All right. Okay. Good luck. So stick around. So I have this survey for you to fill out, but I have to leave the room. So we'll collect the survey. Any leftovers, you get to make it other times. Oh, your makeup exams are online. No, I need them by Thursday, so I could